This time we're going to be looking at Google's billion-dollar eigenvector, and then quickly at eigenvectors and finishing up with what you should know in terms of your vocabulary. So a number of the slides here are going to be based on a talk from Larry Page and his group at Stanford InnoLab in January of 1998. This is the Pagerank citation algorithm bringing order to the web. So at a high level, if we think about what Google did, they actually had a couple of important things when Google got launched. They recognized the need for a new kind of server setup. They had a bunch of hardware stuff they also did that's really cool. We're not going to talk about that. They linked a bunch of PCs to quickly find each query's answers. That resulted in fast response times, greater scalability, and lower costs. And all that's important to what makes Google work. They use now, back then I don't remember, but they use 200 or so different signals, including the PageRank algorithm, to determine what pages are important to your search. And then Google performs a hypertext matching after they get the set of those. So if we think about what a Google search does, you have a query, it goes to a Google web server. The web server sends that to an index server that inside that has the contents to quickly look sort of the material that's in it, comes up with things that match it. The index servers, once they find these are the top documents, sends it over to the document server that actually retrieves the stored documents. Snippets are generated to describe the search results. So every time you search in Google, you see a little bit of text around your search query. And then that's returned to the users, and all this has happened in a fraction of a second. The part we're going to talk about today is mostly about how we're going to help rank them. But the web, to do that, the web's going to crawl the web. The web's out there. They build a program that runs through the web, finds a page, finds all the links on the page, goes get those links, continues. That builds a repository of web pages. Those repository elements are then sent to an indexer that builds a set of content and some structures. So later on, when the user makes a query, we can use the structure to rank what the users asked for and give you the content. So the World Wide Web is very, very large and very heterogeneous. Finding stuff is tricky. And so how can we find the most relevant pages to be ranked at the top? Why do people like Google's ranking better than lots of the other ones? Most of you aren't old enough to have lived through the days before Google, but there were lots of other search engines, and Google quickly dominated in part because they had a good way of saying what was relevant. So let's see how we're going to get there. Let's look at the structure of the web. So I have a web page, and on that web page is a link to another web page. In this case, B is a web page, also links to C. So A and B are what are called backlinks of C. They are pages that point to C. And every page has some number of forward links, outer edges, like the red arrow from A, and backlinks, in edges, the C, the arrow pointing into it. We can never know all the backlinks of a page, but we can always know its forward links. So if I go to a page, I can find everything that points out of it. The only way to find what points into it is sort of crawling the web and sort of keep track of all the outward links and then build a graph out of them. And one of the important insights of PageRank, of what made Google Google's search engine, is the idea that a page is more important if more pages refer to it. And more important people referring to it makes it more important. So a method for computing this rank is to look at this. A page has high rank if the sum of its ranks of its backlinks is high. So if I have lots of backlinks, and if I have a highly ranked backlinks, then my page becomes more important. If somehow CNN points at my page, is more important than if I've written a blog and no one ever points to it. PageRank is a link analysis program that's going to assign these weights. In a sense, the web is sort of democratic with some weights for different things, how they go together. And then Google is going to interpret that. Now, PageRank is not the only thing that Google cares about, but it is very important. And so it's sort of important that we go looking at how we're going to do this. So the way we just described it, if I have a function that tells me all of the pages that link into a page, then if I have this ranking function, I can now compute my rank. The problem that comes up is this is actually a graph. So A points to B, B points to C, C points to A. Now I have a bunch of ranks. But given some set of given a weight vector, I can normalize it, compound how many things are going in and out of the pages that point to me. So BU is my set of backlinks. Take all the things that point to B, in this case it's just A, normalize them, multiply a constant, and that gives you my page rank. And you can do that for every page. But B's page rank depends on A's page rank. A's page rank, oh look, C is pointing at A, so C's page rank affects A. What's C's page rank? C's page rank is pointed to by B. And now we have a problem, right? Or what might seem like a problem. We have a graph that has cycles in it. And what we really want to know is how the page rank affects everything, but everyone's page rank affects everyone else. But the high-level problem are that a page rank is the sum of the ranks of its backlinks. Pages coming from important pages convey importance. So besides the cycle, which actually we'll fix last, there are two other things we have to worry about, what are called dangling links and rank sinks. Okay, so if I start propagating through this, I have a weight 100. I can split my weight into 250s and give it to 2 pages. Here I have a page of rank 9. I split it up into 9. The divisor is because I divided by n of u in that formula. So I'm splitting or spreading out my page rank. That part works pretty straightforward as I propagate links in the graph. But what happens when I get to a page that has no outgoing links? So it got some page rank in, but it didn't go anywhere. Well, it turns out that these pages don't affect the ranking of any other pages directly. They have a rank coming in, but they're not part of the cycle. So it's not really clear where their weight should be distributed. So what we're going to do to make this part simpler is we're actually going to remove them. So imagine finding all those pages that have no outgoing links and deleting them. But if A pointed to C pointed to D, which isn't here on the slide, but if I did that, then after I delete D, then C no longer has a page rank, an outgoing link. So I have to delete it. So I recursively delete all the things that don't point to anything. So in the end, I'm just left with the cycles that are in the graph. So in this, say pages cycles are pointed to by some incoming link. But now imagine we have this link. And so if I have an incoming link and all that I have is a cycle, every time through the loop, things just keep going up and they don't really necessarily increase. So what do we do with this? Well, Google had an interesting insight. They're going to use this idea of what's called the random surfer model. And the random surfer model is that if you're surfing on the web and you get in this loop, you're not going to keep this loop forever. You're going to periodically get bored and jump to some other random page. So it doesn't matter if there is a loop. You might go through the loop once, maybe twice, but then you're just going to jump someplace else. So instead of having our rank be just the rank formula we had before, we're going to add one new term, which is a vector over the web pages, which is our chance of randomly jumping someplace else. So every page's rank has both the rank it gets from its backlinks plus a random chance of being jumped to and effectively jumped out of. But as I said, we still have this issue that this is a page rank, R of U, but it depends on R of V, which is just everyone else's things. So effectively, if I think of R as a vector for the entire web, R depends on itself. In fact, it depends on itself that we can put in matrix notation, and maybe you'll see structure here. So I'm going to say that R is equal to C times A plus E times the identity matrix. Sorry, that should be an identity matrix, expanding it out, times R. So now I have this structure. And so what is A? Well, A is just the backlink matrix, put into a big matrix form. So it's looking at the chances of those moving forth. So my page rank depends on this link structure stuff with a normalizing constant on my page rank. Does that strike you of anything? Well, if you think of this as a matrix, right, this looks like something where R depends on R. If I rearrange these terms, you'll see that this is an eigenvector equation. And you can actually show that for this structure, because of the way A is a transition matrix without the weights, that the largest eigenvalue of this vector is 1. So R turns out to be the dominant eigenvector of A plus E times 1, right? So this expanded matrix, right, is a matrix, and I basically, if you think of this is lambda. It's actually the whole set of eigenvectors, but lambda is our eigenvector. Lambda A plus EX1 equals lambda X, right, or just lambda. So because the largest eigenvalue is 1. So R is our eigenvector. So how do we build PageRank for the web then? We're going to convert each of the URLs into a unique integer. And we're going to do that in part just so we have a nice structure. We're going to sort the link structure by that ID. So we're going to sort them so we have them in some order. We're going to use that to remove the dangling links. So we're going to iterate through removing anybody who doesn't point to anybody. Make an initial assignment of ranks. And that can actually be just random numbers. It doesn't really matter. Or it could be last year's ranks. It doesn't matter. We're going to iteratively compute the page rank until it converges. We're going to add the dangling links back. And as we're doing that, we have to remember to iterate as many times required to remove the dangling links. So before when I had C point to D, that took 2 iterations to remove. Then after I put the dangling links back, that would say I have to iterate 2 more times to converge the PageRank and get the final answer. Sort of looking at it as computing the PageRank vector, the actual vector itself. I start with any vector, and some random assignment of the weights. I'm going to calculate A times Ri, the current estimate. I'm going to normalize those, and it's important to normalize them. Otherwise, as you remember from eigenvectors, right, we want them to be normalized. In this case, we're going to compute the normalizing factor. We're going to add that into our E, our random surfer jump model data, and add that in. And if you look here, you're just going to see this is A times R plus E. So we're just doing it slightly different than the formula, but this is an efficient way of doing it. And then we're going to ask, did we change much from the last iteration? If we did, we keep going. If we didn't change much from the last iteration, then we say we've converged and we're done. So now this sounds very simple. This is a variant of the power method for eigenvectors. Now if we look at this, how fast does it converge? So this is actually from their original paper back in '98. Back when they did some testing with 322 million links in the web, this process converged to a PageRank after just 52 iterations. And for half that, at 161 million links, it did 45 iterations. And roughly, the convergence factor seems to be log n, where n is the size of the internet. Again, just to sort of see this as a graph, I'm going to walk through it in a little bit more detail just so you can see the eigenvector and how to build these matrices. So we're going to assume they're ordered, which we've already done. We talk about inlinks and outlinks. So if there is in our matrix, in this matrix here, we have a 1 saying in the location 1, 2. So this is saying that 2 points to 1. Down here we have in location 1, 3, we see that 1 points to 3. We also have 3, 1, 3 points to 1. Links in the web don't have to be symmetric, so this matrix is not symmetric. But this forms what we call our adjacency matrix. And the diagonal should be 0 because pages shouldn't point to themselves. So now what do we do? Well, we can define a bunch of rules, but what we're going to end up doing is we want to normalize these. In this case, we're going to normalize every element by the total number of pages in the link. So this just gives us the average out weight. So if I have a total of 9 links coming in, or weight coming in, then I'm going to divide by 9 to send them back out. So in this sense, what comes into my page goes back out of the page, and that gives it a nice structure. Turns out this is a general form of a more general concept of what's called stochastic matrices. The columns have non-negative entries and always sum to 1. So every column sums to 1 because we've normalized them. Every column is effectively divided by its sum, so they all sum to 1. So if that's our original adjacency matrix, the stochastic matrix, where we've just divided each column by the sum of each column, looks like this. And now we're going to find this by finding the eigenvectors. So we're going to find R, the eigenvector, equals D times R, where we take our stochastic matrix and put it in. Again, this does not have the escape vector, but that just adds one more step where you add it back in as you're doing the technique. And as I said, the Google PageRank estimation is actually a power method technique to estimate the rank and move it down. So if I go back to this matrix and I forget the escape matrix and you iterate through this, you end up finding that the eigenvector is 0.6, 0.3, 1, and 1, so that page 4, this one here, number 3 has the highest rank, which you can sort of see. It's got 2 incoming arcs, 2 outgoing arcs. These others only have 1 incoming arc, so they have less, and they end up getting less weight. So in the real world, of course, things are a lot bigger. In fact, things are bigger than when Google started. The web now has about 50 billion pages. That matrix is by far the world's largest matrix to be used on a regular basis. Luckily, it's mostly 0, so it's a sparse matrix. So in fact, there's specialized techniques for computing those iterations where you don't actually even store the entire matrix. You can imagine this matrix, if most of it is 0, maybe I don't store the matrix, I store the locations that are not 0, and then you can work out more techniques. The image that was at the very beginning of the first video was a Google matrix for about 3 million pages. You can just look at the brightness and you can sort of see how asymmetric they are. They're structured all over the place. And There's a lot of magic inside of Google we don't get to know. There's a lot more rules, and to make this robust, a numerical method, make it fast, especially if you want to update your PageRank for 50 billion web pages pretty much every day. So you got to do it fast. So the last thing we want to talk about for this chapter is the idea of eigenfunctions. We've talked about eigenvectors and values, but if we're actually talking about functions and function spaces, what can we do? So if I think of a function f, y equals f of x, and they're real numbers, and we assume for a second it's smooth and differentiable, for example, the sine of x, it turns out that the set of all such functions form a linear space. It's a space where instead of a point being a number, a point is a function. And I can take linear combinations of functions. If I add sine and cosine, I still get a function. So all of those is a space of functions. And we can generalize even further and talk about linear maps on these functions. So for example, the derivative is a linear map on top of the space of functions. I can take the derivative of cosine, sine, and get cosine. The derivative maps one function to another function. And if the original function is differentiable, the derivative function is differentiable, and so on. So it has all the right properties of being a linear map. It's now in this very high dimensional space. And if this seems really abstract for you, don't worry too much. I'm introducing it because some of you may go into parts of computer science where you end up using this space, so you at least have seen some of it. We won't actually do any of this for programming assignments or deep questions, as long as you know the terms that we're talking about for eigenfunctions. So D will not have eigenvectors since our linear space consists of functions. It doesn't have vectors, it has eigenfunctions. And what do we mean by an eigenfunction? Well, if we go back to the thing that defined eigenvalues, we had some a times x equals lambda times x. Well, instead of x, we're going to use f. D times f equals lambda times f. What's a function such that if I were using, for example, the derivative map, right, the derivative of f is equal to lambda times f. Right? That's straightforward to think about. So if I think about that, it's not hard to see that the function e to the x satisfies that property. So if I take f prime as my, if I'm taking derivative as my map, then f prime of x is equal e of x. Right? If e of x I take its derivative, in fact, if I have a constant up front, I actually get a lambda down front. More generally, any function of the form e to the lambda x gives me the derivative is equal to lambda e to the lambda x. Okay? So d of f equals lambda of f. Exactly what we saw for eigenvalues and eigenvectors, except now we're doing it with functions. And this is true for all real values of lambda other than 0. So even though not only we're talking about functions, before we had a finite number, if we had A was an n by n matrix, it had at most n eigenvectors. For functions, the corresponding eigenfunctions are infinite. D, the map D, the derivative map, has infinitely many eigenfunctions because it's true for all values of lambda, 0.1, 0.2, 0.2, 0.001, whatever, all of them. Okay, we can go further. We can talk about the map of second derivatives. So the second derivative map is equal to some function. A set of eigenfunctions for this map turns out to be cosine of kx for k equals 1, 2, 3, 4, 5, 6. And the eigenvalues are minus k squared. And you can do this by saying, look, if I take the first derivative of cosine, I get sine. Take the derivative of sine, I get back to cosine, except I get minus k squared out in front. So eigenfunctions, can be found for lots of different linear maps over the space of functions. Now you might be wondering, why in the heck does anyone care? Well, it turns out that eigenfunctions have many uses. If we think back to the idea of an eigenvalue, an eigenvector, eigenvectors are the directions in which things don't change as I reapply the map over and over again. They become sort of stationary directions. If we think all the way back to the Tacoma Bridge and those variations, those were modes of vibrations of mechanical structures. It turns out that, in fact, not just eigenvalues and vectors, but really eigenfunctions are what we use to analyze those things. They're used very often in differential equations as ways of structuring the rate of growth of mechanical systems or processes, biological processes. They're also commonly used in mathematical physics and engineering mechanics and mathematics. They lead to this idea of orthogonal functions for data fitting and vibrational analysis. And these vibrational analyses are what one would use in those kinds of bridge questions. And they actually arise out of the Sturm-Liouville equation, the second derivative of x plus lambda times, second derivative of y with respect to x, plus lambda times y of x equals 0, where we want to have an initial condition that it starts at 0, and then at the end, at pi, it has to equal 0. So this is sort of like a periodicity equation. And that leads to all kinds of vibrational analysis, stable modes of vibration and stuff. It's also used a lot for second-order differential equations with boundary conditions. And by boundary conditions, what we really mean is you have a function, you have to satisfy the derivative, but you also have to hit some values at the end. It turns out that for these kinds of boundary value problems, eigenfunctions of the Sturm-Liouville equation gives us parts of the solutions. And for example, for this example of y equals sine of a of x, the corresponding eigenvalues are lambda equals a squared, and the eigenfunctions come back to be themselves. So we get sines. So lots of different kinds of problems. And again, if that's all over your head, all that you really need to know for this chapter are, with respect to that last star from the eigenfunctions, is we'll be able to write down this equation for an eigenfunction and explain what they are with functions, and also know for sure that you can have infinitely many of them. So you might be able to remember this for the derivative map. Okay, so the other terms you need to know from this chapter, going all the way back, this is the third of 3 videos, eigenvalues, vectors, characteristic polynomials, properties about eigenvalues and eigenvector symmetric matrices, dominant eigenvalue, eigendecomposition, right? Every eigensystem, every symmetric matrix, you get R lambda R transpose. The idea of a trace, the sum of the items down the diagonal, how that gives you a bound on what's going to happen with the eigenvalues, how eigenvalues are related to quadratic forms and positive definite matrices, the power method of computing, iterate to find the largest eigenvector, the idea of the max norm, which is what we use for normalization during a bunch of these processes, where you find the largest value in a column and you divide by that, or you can do the sum, which is the L2 norm, or L1 norm if you just do the sum. Sum of squares would be L2. Understand the ideas of basis vectors and the eigenbases, how we use those in principal components and sort of eigenfaces. For the Google matrix, make sure you understand the idea of adjacency matrices, a directed graph, the stochastic matrix, and the stationary vector we get out of that as our sort of rank matrix. I know this was a lot of material for this week. We'll be applying some of this for our second program. Eigenvalues and eigenvectors are one of the important concepts you get out of